Hello, welcome back. In this segment, I will show to you how to combine the Sieve of Eratosthenes algorithm and the randomized primality testing algorithm. For example, Fermat-Euler or Miller-Rabin, okay, as randomized primality testing. First of all, you may wonder, why do we need to combine? We were able to successfully use Sieve of Eratosthenes to generate a list of primes. Um, Similarly, we were able to test whether a number is prime or not using um, Robin Miller or Fermat-Euler. Why do we need to combine? Well, if you think about it, Sieve of Eratosthenes itself is not a scalable algorithm. Its complexity is exponential in the length of the input. Okay, so we can't use Sieve of Eratosthenes as it is. What is the limitation with the randomized primality testing? One of the limitations is that we will do a random number of atoms and apply exponent operations in model arithmetic. Okay, so in order to speed up randomized primality testing, therefore it makes sense to first collect a small list of primes using Sieve of Eratosthenes. For example, the first 2 power 16 numbers, what are the primes from 1 through 2 power 16? 2 power 16, okay? We put it in a list and we use that list to check whether any of the large numbers, okay, is divisible by our prime that is in the list produced by Sieve of Eratosthenes. Okay, let me show you the demo and then talk about the algorithm directly. All right, let's get it started. So first, let's generate, say, 2 power 16 primes, okay? Okay, let's get started. Let's first generate all primes until 2 power 16, including 2 power 16. Okay. So now we know for sure this list, which has how many elements? 6,542 elements. They're all primes for sure. Okay, because Sieve of Eratosthenes is producing primes with 100% guarantee. Okay, there's no uncertainty whatsoever. All right. And now we will use the list of primes we just got from Sieve of Eratosthenes to speed up the computation using, say, Miller-Rabin. Okay, let's do that very quickly. Let's assume we wanted to call Miller-Rabin let me start with some small number first. Let's say generate a 256-bit random prime number using Miller-Rabin. Now I'm not using the primes, right? In this random prime algorithm, I'm just specifying Miller-Rabin. 80 is the number of atoms Miller-Rabin will do. We talked about it in detail earlier. And 256 is the size of the prime we would like to get from Miller-Rabin. So we got one immediately. And if I now go and combine it with Sieve of Eratosthenes, and I have to send the primes, you got the same answer very quickly. There's not much difference, but let me increase the size and you'll see difference soon. Let me make the random bit size to be 512. Okay, so we are going to ask for a 512-bit random number through Miller-Rabin. But now let's use the same, but together with Sieve of Eratosthenes. Okay, that means I have to use my SE. The name ends with SE means I'm under the hood combining with Sieve of Eratosthenes. Okay, you probably saw not much difference, although it's slightly fast. Let us increase the limit further. Let's say, give me a 1024-bit number, a prime number. Okay, now it's generating a 1024-bit prime number. Okay, we got one. Now let's use the regular algorithm without the Sieve of Eratosthenes combination and see whether we are seeing any difference. Okay, probably you saw somewhat slow when I used the regular Miller-Rabin without Sieve of Eratosthenes. Let's increase the size further, then the difference should be more apparent. Let's say I am going to use 1536-bit prime number. Okay, I'm going to generate a 1536-bit prime number without using Sieve of Eratosthenes. It's going to take some time. You'll see. Okay, it took some time. Now let's look at the same algorithm, but we will combine it with Sieve of Eratosthenes first. Okay, and we need to pass the list of primes that we got from Sieve of Eratosthenes. It's slightly faster when we combine it with Miller-Rabin and the Sieve of Eratosthenes. Okay, you probably noticed that we got the answer relatively quick comparing to just calling the Miller-Rabin. Okay, that's basically the main message of this video. Now let's look into the algorithm, how we combine Sieve of Eratosthenes with Miller-Rabin. So I will show you the algorithm. So here is the algorithm. The algorithm takes a few parameters. Let me explain this first. B is the bit size, like how many bits you want in your prime. And the primes is the list of primes you got from Sieve of Eratosthenes. If you send in an empty array, the algorithm under the hood calls the Sieve of Eratosthenes. Of course, this is inefficient when you keep calling this like this. It's better to compute the primes once and leverage it. That's the reason I pass it as an argument. Okay, and then you could specify what algorithm you would like to apply. Is it Miller-Rabin or Fermat-Euler, and the number of trials. Okay, and what we are doing here is that we have this outer while loop. We randomly pick an odd b-bit number, right? And then we leverage a number theory result. It's called Bertrand's postulate. There is a prime between any two numbers r and 2r, meaning say r is say 5. That means between 5 and 10, there is clearly a prime, number 7, for example. Okay, so that's the prime postulate that we will use. So we start with the random r, odd number, of course, and we check whether the size of the bits, the bit length of the prime, the potential prime p is less than or equal to b. Meaning, if it exists b, we say, well, that's not a good p, because we need to satisfy the requirement that we need a prime to be bit size of b. Okay. We also check whether the prime b, the potential prime p that we generated, is in the primes list. If it is, then we don't need to do anything. We just return the prime. Otherwise, what we do, we check whether any of the primes in the list of primes is actually dividing our candidate prime p. If it is, then of course we know for sure the prime p cannot be a prime. The candidate p cannot be a prime because there is some prime that's dividing it. Then we move on to the next attempt by incrementing the prime to be the potential prime candidate to be 2, and we continue this loop. Okay. That's basically the idea of this algorithm that combines Sieve of Eratosthenes with Miller-Rabin. Okay, let's assume we generated the random odd number r, and we check that none of the primes in the prime list is dividing our random r. Then we go ahead and call the algorithm. The algorithm is, remember, Miller-Rabin. Okay, in this case, you could also use Fermat-Euler or anything else that's supported. So essentially, that's what's happening. First, check whether your random number is divisible by any of the primes you have. If it is true, then you know for sure your random number cannot be prime. If none of the primes is dividing it, then you can go ahead and apply your fancy Miller-Rabin or Fermat-Euler or whatever algorithm. So this is one interesting way to combine Sieve of Eratosthenes, which is very good algorithm for a small list of primes that you could use to filter out potential large candidates before you apply before you apply Miller-Rabin or Fermat-Euler. That's all I want to share with you. Thank you very much.